Good morning, students. Can you hear me?
Yes.
Yes, sir.
Okay. Now you can see the Hall effect setup, and I now switch on this Hall effect setup. There is a digital display in Hall effect setup by which you can measure the Hall voltage and current which is passing through the semiconductor. And there is a particular knob by which you can use the same digital meter to measure the current and voltage. Now I turn this knob towards the current side. Now you can see the milliampere LED is glowing, and you can measure the current from the digital milliammeter. And now the current is showing 2.98 milliampere. And when I change this knob towards the voltage side, this same digital meter is showing the voltage in millivoltage. Okay. First of all, you have to set a constant current to the semiconductor by turning this knob towards the current side, and it may be 3, 4, any value of this particular current. Now I start this experiment with 2.98 milliampere current. Then I turn this knob towards the voltage side, because throughout the experiment this current remains in 2.98 milliampere current. You do not need to change this current further. And now I move into the electromagnet power supply or coil current supply. Uh, I switch on this. You can see there is another digital display in coil current supply, and another knob is here by which you can change the coil current by turning this. You can see the gradually current is increasing. First of all, you have to set it in zero, or you can switch off this. That means the zero coil current is now supplied to the electromagnet. This is the electromagnet, you can see. And what will be the magnetic field present at the center of the electromagnets? Because the coil current is zero now, then there is no magnetic field present at the center. Where is the actually Hall probe is placed? There is a Hall probe. One probe is actually for magnetic field measurement. Another probe is actually for the semiconductor. These magnetic field measurement you can measure by the digital Gauss meter. This is a digital Gauss meter. If I turn on this digital Gauss meter, you can see there is a digital display by which you can measure the directly you can measure the magnetic field. That is now it is showing 3 Gauss. There is a zero adjustment knob by which you can make it zero. But if it is very close to zero, it may be 3. You just note down this is the initial value or initial error present in the digital Gauss meter. So you just note down for the zero coil current of the electromagnet, the magnetic field present is 3 Gauss. And further, when you are measuring the another magnetic field, you have to subtract this initial error from that value. Now I switch on this. First of all, there is another reading you have to note down. That is the initial Hall voltage, which is showing minus 0.4 millivolt. You have to also note down this value. This is also initial error present in the Hall voltage. This is for zero coil current. Now I turn on this coil current. The second observation for 0.1. You have to make it 0.1 ampere. Then move to the magnetic field, where you can see this is 62 Gauss. Actually, this is showing 62 Gauss. You have to note down for 0.1 coil current. The magnetic field will be 63 Gauss. And what will be the Hall voltage now? Now the Hall voltage is minus 1.1 millivolt. Okay, this is the second observation for you. Now again you have to change the coil current to 0.2 ampere. Okay. Then again note down the magnetic field. For point 2, there is 130 Gauss. And again, note down the Hall voltage, which is now minus 1.9 or 1.8. Okay, 1.8. Okay. So this is the procedure how you can note down the reading for different coil current. Okay. Okay. Now আরেকবার বলো তো? Okay. পুরোটাই? The observation কি কি লিখতে হবে? Okay. Now again I am telling you, just you have to change this coil current one after another, that is already written in your manual, like 0.1.2 up to 1 ampere. First you change this coil current for a specified value, that is now point 2. Then you have to note down the magnetic field for this point 2 coil current, that is 130, and simultaneously you have to note down the Hall voltage also for this point 2. These are the three readings we have to observe. Okay.
Thank you, sir. We'll now discuss how you use this data to estimate our Hall coefficient. So, as sir has mentioned, that first the current through the semiconductor is fixed. As for example, say it is fixed at 2.8 milliampere. You have obtained your data set. In the data set, you will observe the value is given to some other value. Next, what sir has done? The coil current, that means the current into the electromagnet, that value is fixed to first 0. That means there is no current passing through the electromagnet. So ideally, if you are not supplying any current into the electromagnet, that means the magnetic field should be 0. But as I has shown you that you may observe some small amount of magnetic field. You may observe some amount of magnetic field in that gauge meter, and that may due to the residual magnetism. The electromagnet has been used before, so it may take some residual magnetism in it, and that residual magnetism you may observe. But it is not correct ideally, because you are giving coil current to be 0. Therefore, whatever value you get at that coil current 0 as your measured value, say you are getting 3 gauge, you make it corrected to 0. That means 3 minus 3, 0. So whatever value you will get for different coil currents, you will subtract the initial value from all of them. So that will be your corrected reading in magnetic field. Similarly, for 0 coil current, you have observed you are getting some Hall voltage VH. Again, when we discuss the theory, I told you that to observe Hall effect, you require both magnetic field and the current through the semiconductor. That means you require this value, the coil current, current through the semiconductor, and magnetic field. Both should be present. But if we are supplying only the current into the semiconductor, no magnetic field, here magnetic field is 0, then ideally we should get 0 VH. But due to some circuitry problem or due to misalignment, we may get some value as measured value. So again, we need to calibrate it. That means whatever Hall voltage we will get subsequently will just We'll subtract the initial value from all these values to get the corrected reading. I'm showing you one reading set. Suppose, suppose this is your data. Suppose after doing the experiment in virtual mode, you cannot do that experiment by yourself. So you have already received the data set. So you will get similar type of data set. Of course, it will be different for you, but similar. So you are for a particular value of current passing through the semiconductor, you are getting some magnetic field as measured and corresponding Hall voltage measured. So you observe here, when coil current is zero, we are getting some value of magnetic field, which shouldn't be there. So how will you make it corrected? We'll subtract 7 from each of these reading, so that first one will be 0 and subsequent values. That means next one will be 99 minus 7 and so on. Similarly, when magnetic field is 0, ideally we should get 0 here, but we are getting some value. So it should also be corrected to 0. That means like this. You observe that was the initial value in Gauss meter. So we have subtracted this 7 from each
Sir,
of
we are
these values.
subtracting the second value with the first value.
You are subtracting this first value from all the values. That means 7 minus 7, 0. 99 minus 7, 92. 161 minus 7, 154, and so on.
Oh, okay, sir.
Similarly, say I'm giving you a simple one. Suppose your measured Hall voltage is 0.5. Initial value should be 0. So you are now subtracting 0.5 from all the values. You are subtracting 0.5 from all the values. That means first one will be 0.5 minus 0, 0.5 minus 0.5, 0. Then minus 2.19 minus 0.5, minus 2.69, minus 3.08, minus 0.5, and so and so. If you get the initial value as say minus 1.2, then you will subtract minus 1.2 from all the values. That means first one minus 1.2 minus 1.2. That means you are adding 1.2 with all the values. So first one will be 0, then minus 2.19 minus 1.2. That is minus 2.19 plus 1.2. It will be minus 0.99 and so on. So from all the values, you are subtracting minus 1.2, the first value. You are subtracting first value from all the values to get the corrected value. So this is our actual or corrected magnetic field and corrected VH. We'll utilize only these two to draw our graph. Clear? We'll use these two only to draw our graph. How will you draw the graph? So basically we require 4 quantities. Remember the theory, if you have written it, to estimate RH you require Z. As I said, it will be given throughout the experiment. I is fixed. So your only variable are B, the corrected B, and VH, the corrected VH. Out of these two, which one is the independent? Because we will plot, remember, for any graph in any subject, whenever we plot two variables, then we need to estimate the relationship between the two variables. Then one must be dependent on the other. We'll plot independent variable along x-axis and dependent variable along y-axis. I'm repeating. We'll plot independent variable along x-axis and dependent variable along y-axis. Now out of B and VH, which one is independent? We know that to observe Hall effect, B is essential. If B is present, then only VH will be observed. So VH depends on B. Therefore, independent quantity is B. Therefore, we plot B along x-axis, VH along y-axis. How will you plot? Let's try. This is our plot. This is the scatter plot. So you have observed that B is positive throughout, but VH starts from 0 to negative values, increasing negative values. So if we plot, it will look like this. So this is your plotting B along x-axis, VH along y-axis. When you plot, remember, whenever you are giving the axis like Hall field B, you must mention the unit. Here we have mentioned unit as Gauss. Similarly, along y-axis, we are plotting Hall voltage. You must mention the unit, millivolt. Okay, without unit, there is no meaning of any value. So if we plot it, these will be the points. We have only 11 points, so we have plotted it. These are the points. Now we need to draw a line so that ideally all points should lie on that straight line. But hopefully from the experimental of points, you can understand that you cannot draw a line on which all the points will lie. It's not possible. So how will you draw the line? How will you draw the line? How will you connect these points to get a straight line? Let's try. Suppose this is your line. If we draw it in this way, you observe some points are connected, no doubt. These 2 points are connected. This point and that points are connected. But you observe most of the other points are on the bottom portion. This is the bottom portion, this is the upper portion. This is the upper portion, this is the lower portion of that line. If we say these are the 2 regions, upper region and lower region, then we observe most of the points are on the lower region of the straight line. Most of the points are on the lower region of the straight line. That means what we observe, that this point should be at that point. This point should lie on the line, but it is not lying on that line. So this is the error. This separation is the error. Similarly, this is a small separation, this is a large separation, this is a small separation, and so and so. So we can estimate the error. So all you observe, we get a large amount of error because all the points are on the lower region of the line. Okay, if we now draw it in different way, let me draw it in different way. So that was the previous drawing. Now we have drawn it in this way. If we draw it in this way, now the color I was showing as blue straight line. You observe now most of the points are on the upper region. Most of the points are on the upper region. So again, these points contribute to the errors because most of the points are on the upper region. They will contribute some error. Only 1 point on the lower region. Therefore, this is not also a right one. This is not the proper way of drawing the straight line. We'll try to draw the straight line in such a way that some points will be on upper region, some points in the lower region, so that total errors due to the points on the upper region, must be balanced by the total errors due to points on the lower region. That means first you just place the points on your graph paper, then place your scale in such a way that you will observe a particular way of placing. In that case, some points will be on the upper region, some points on the lower region, if the points are not lying on your straight line. If the points are not lying on your straight line, then the line should be drawn in such a way that some points will be on the upper region, some points will be on the lower region. That means this is not correct. This is not correct as well. So how will you draw? This is the fit. This is the proper way. You observe if some points are on the line and some points on the left, some points on the right, such that total error due to the points in the lower region is balanced by the total errors of the points on the upper region. There is a scientific way of drawing it by estimating the slope of that line also. We'll discuss it in other time. First, you try to draw it by yourself, just looking at the points. So if we can fit, and of course you understand, different people will draw it in different way. So slope will be different, no problem. That means your answer will be different. But you try to draw it by yourself. Then if you are satisfied with your straight line, then what you will do, take any arbitrary large value of Hall voltage, Hall field, that means B. Take a arbitrary large value of B which is not in your data set. Like say I am taking 500, I take 600, I take 700, say. These points are not in your data. Say for 500, we want the value of VH. So we fixed B as 500. So B is our now 500, this value. And from the graph, from this straight line, we can estimate what will be the value of VH for this value of B. What will be the value of VH for this value of B. So we are not estimating BVH set from our data set. We are determining VH for a particular value of B from the graph. So if I assume that B is 500 Gauss, then VH will be estimated from the graph. So from the graph we are getting V value as minus 8.2. So if we have these 2 points, then this is our VH by B from the graph. If we estimate VH by B from the graph, then rest calculation is very easy. So rest calculation, what we require, this Z is supplied, this Z value is supplied 0.05 centimeter, that means 5 into 10 to the minus 4 meter. We have fixed the current into the semiconductor as 2.8 milliampere say. And from our graph, we have estimated VH by B as this value in millivolt per Gauss. Then for our estimation of RH, we require Z by I into VH by B. Z given, I we have fixed to 2.8 milliampere. We have already estimated VH by B from graph. So now you just put the values. So Z 5 into 10 to the minus 4, all values should be in SI units. So Z will be 5 into 10 to the minus 4. I 2.8 milliampere. So ideally we should write 2.8 into 10 to the power minus 3. Because we know to convert milliampere into ampere, it will be 10 to the power minus 3 ampere. So ideally we should write 2.8 into 10 to the minus 3. But you observe VH is also in millivolt. VH is also in milli. VH is also in millivolt. Therefore, this 10 to the minus 3 cancel out. That's why I have not written it here. So 2.8 they are fixed. Next VH and B, you estimate them from the graph. Now from the graph, B you estimated as 500 Gauss. Gauss is not an SI unit, so you need to convert Gauss into Tesla. 1 Gauss equals to 10 to the minus 4 Tesla. 1 Gauss equals to 10 to the minus 4 Tesla. So put that value. Rest is easy. 10 to the minus 4 cancel out. Calculate this value. You get RH. So this is the way you can estimate the Hall coefficient. Next part will be discussed by TRC sir. Sir.
Okay, good morning, students. So, sir has discussed about how to calculate your Hall coefficient from the graph. Now, one thing I would like to add what sir has said, that your graph must pass through the origin. That while connecting the points, while you are drawing the mean graph, that is, sir was saying that there must be equal number of points lying below the line as well as above the line. But while you are drawing the graph, keep it in mind that in this case, the graph must pass through the origin. I'm circling it. The graph must pass through the origin, because you see this is all field in the x-axis, that is the magnetic field that you are applying, and on the y-axis you are getting a Hall voltage. So if you do not, ideally, if there is no magnetic field, there should be no Hall voltage as well. So your graph must pass through the origin. So keep it in mind that there are two things. There must be approximately equal number of points lying above the line and below the line, and the graph must pass through origin. So you have chosen a point. Sir has chosen this point. You could have chosen this point. You could have chosen this non-experimental point. So if this is your point, then your corresponding B is 650 Gauss over here, and your corresponding VH would be somewhere here, that is around minus 11 millivolt. So accordingly, you will put VH as minus around 11 volt, and this would be around 650 Gauss, and you'll convert it into Tesla. So it's up to you which point you choose, but our suggestion is choose a point on the higher side of the line. So this is how you get the Hall coefficient, and you can see you do get a minus sign over here, which implies what sir was telling you, that this implies your semiconductor is an n-type semiconductor. So now again we move on to the error calculation. So RH was calculated, VH by B, Z and I are given to you. RH is calculated from the graph between VH and B, and this is coming out to be this. So you know from the what is the proportional error? We know the relative error or proportional error. We did it in the previous day. So again, we are running out of time. So once it ends, you will again rejoin using the same link. So the proportional error in the Hall coefficient, you can see delta RH by RH is equal to Z and I are constant. Z is the thickness of the material, which is a constant. I is the current that you are supplying through the semiconductor, it is a constant. The only variables are VH and B. So you know from the error calculation, delta RH by RH is equals to delta VH by VH plus delta B by B. Now what is delta VH and what is delta B? Please understand, delta VH is the smallest unit along the VH axis, that is Y axis, and delta B is the smallest unit along the B axis, that is magnetic field axis, that is the X axis. So I'll show you something. Let us say, okay, let us see this graph. Let us see this graph. Let us look at this graph. Look at this graph. So you can see this is the x-axis. This is the x-axis, that is b-axis. So these, if you when you are drawing your graph, you have 10 small divisions over here. So this is up to you how you scale your graph. For example, you have drawn your graph like this, then you have 10 small divisions, and you have made, or you have written this as 100. So your 10 small divisions in x-axis corresponds to 100 Gauss. So what is delta B? Delta B, as it is mentioned, it is one smallest or the smallest unit along the x-axis. The smallest unit along x-axis in this case will be 10 Gauss, because 0 to 100, 100 to 200, and between or in between each 100 Gauss, there are 10 small divisions along your x-axis if you draw it like this. So one small division will be equal to 10 Gauss. So delta B would be 10 Gauss. Similarly, if you look at the y-axis, that is the Hall voltage, again there are 10 divisions. Again there are 10 divisions. If you see your graph, then again there are 10 divisions. So 0 to -2, let us say, again in between there are 10 divisions. So one smallest division, that is delta VH, that I was talking about, is equal to minus 0.2, because two divisions in between 2 millivolt, there are 10 small division. So one smallest division is equivalent to minus 0.2 millivolt. This is delta B and delta VH. And what about this value? What about B and VH in the equation? This is the value of B. You can see the value of B is from your graph, the point that you have chosen. In this case, we have chosen this point. So B is 500 and VH is this around, it's greater than minus of 8, maybe it's minus 8.2. So you can see it is written over here. So you can see VH is minus 8.2 and B is 500 for the point that you have chosen, right? You could have chosen, again I repeat, you could have chosen this point. For this point your VH and B would have been different. So coming back to what I was saying about error calculation, so if you look at the error calculation, so you can see delta RH by RH is delta VH by VH. Delta VH is the smallest unit along the y-axis, and as it is seen, it is minus 0.2. VH is the Hall voltage of the chosen point, that is minus 8.2. In this case, you could choose it differently. Delta B is again one smallest division along x-axis. That is how you scale your graph. In this case, it is 10, and B is the magnetic field of the chosen point, that is 500. So what you get is, you get this as delta RH by RH. So what is the absolute error? So what is the absolute error? The absolute error is delta RH. And what is delta RH? You have to multiply this delta RH by RH into RH. You get delta RH. So you multiply these two, and you get delta RH. You get delta RH. So you multiply this value and you multiply this value. See, your calculator will show many decimal places, but you need to truncate your result up to the required digit. So delta RH, if you multiply these two, you will get something like this. This is your delta RH. Now please see, if you add and subtract delta RH from RH, that is, if what I want is, I want RH, that is Hall coefficient, plus minus the relative error in the Hall coefficient, delta RH. So if you add and subtract, add or subtract this from this, then which is the first digit that is getting affected? So you can see here 0 0 is there. So 0 and 2 will not get affected, because if you add or subtract 0, you will not, it will not change. 1 is there, it will affect 9. It will affect 9. So which is the first digit that is getting affected? 9 is getting affected. So you cannot write beyond 9, because you are not sure about 9. You are uncertain about 9. 9 will change. You are sure about 0 2 because of that, this error, but you are not sure about 9. 9 might change to 8 or something else. So you cannot write all these digits. You have to truncate your result till 9. So this is what you get. You can see here the result has been truncated to 9 with a bar above 9, as we were explaining the other day. Bar means you are not sure about 9, but you're sure about 0 and 2, plus minus the absolute error, that is 0.001 meter cube per coulomb. This is the value of RH. This is the value of RH that you are expected to get. So what we are doing is we have supplied you, already mailed you the data. Work with your data. In your data, I might be different, the current through the semiconductor, Z is same. Plot the graph. So before plotting the graph, as sir was mentioning, you need to calculate the corrected value of magnetic field and Hall voltage. Use those corrected values of magnetic field and Hall voltage, plot them, draw a straight line uh, using the technique that sir was mentioning. Here the number of points above the line must be more or less equal to the number of points below the line. Choose a point on that line, an arbitrary point on the line. It's your choice, but it should be a non-experimental point. Choose an arbitrary point. With that arbitrary point, you'll get that value of VH and B. Put that value of VH and B in this equation and find out the value of RH with SI units. Please convert Gauss to Tesla, and Z is in centimeters, convert it into meter, and find out the value of RH. Then using your graph, find out the value of delta RH by RH. A group has been created for physics lab. Now the session is ending. We are going to start again. So please log in using the same details. We will discuss. Please draw the graph using pencil and graph paper. Do the calculation and show it to us right now. We are here to help you out. Whatever problems you have, discuss with us. And if you have problems, then there is a Telegram group where you can write your problems. We'll address the issues. So it is ending right now. So please rejoin using the same link.